All right, what's up, fam? May 10th, 9:30 p.m. around. Back at it again. I think it's day 39. Um, Waiting to hear back from the interviews. And then after this question, I have to learn about networking because I have to help my girl with her homework. Pretty exciting stuff, pretty fun. But today I learned about topological sort. So it's basically like saying if there is a cycle in the graph, then there's no way you get an order, right? Because they depend on each other. And another name for that is like strongly connected components. So these are like isolated components of the graph where if once you leave the one of the nodes, there's no way of getting back. Um, yeah, and so topological sorts only work with acyclic directed graphs. If it is cyclic, meaning there is a cycle in it, then you're fucked. Then there's no way of finding a order. So I think this is what we're trying to do here. Um, is that is to basically and to do a topological sort, you would want a stack. So I'm thinking. For this one, I'll put in the list and then I'll traverse it depth first. And if the node exists within the stack, then I will then I'll return false, right? I think. Um yeah, so I feel like okay, so this is to make the adjacency list, right? This part I don't think is wrong. And then this one I feel like is also true, right? You want to keep track of, right? Which has been traced, right? So I'll write a, I will take a vector of bool visited, and then it will also take a adjacency list, which is like graph, right? And then it will also take what exactly? And then I'll call this on. Can I show my love for you? I think if it's okay, if I take, can I do this without? I can also do it via BFS. I do think I can do it via BFS. Um, so I keep track of this, and then for in I equals 0, right? I is smaller than adjacent size. This is fine. And then if I put every neighbor in a stack, and then I'll check if the stack has been if what are some other test cases? What are some other test cases? I want to see a test case that is a better test case per se. Okay, there is no better test case. Right? Yeah, I mean it is. I just don't know how to write the DFS. I think DFS makes the most sense. Um, so if I just go DFS, right? Bool DFS, and then it will take this. That is for sure, right? It'll take a graph. Um, it'll also take a stack, right? Stack and call it stack. And this will be a stack of ints. This will have to be a reference. DFS. What else do I need for a DFS? Um, should this be a graph? Because the recursive call is only a vector, right? So maybe I should call it a vector instead, right? Right, right. Topological sort algorithm.
Posting track again. Here's some pseudocode.
Right, visited, I do have. Ordering. Well, this is the result, so I'm not going for the result here. For, okay.
Jason, return slide there disclose message.
What is a DFS logic?
And but this time,
Huh. Um, In at visited. And then visited nodes will be the stack, right? I'm quite confused, to be honest.
actually the state memory function for search method.
Okay, detect cycle in directed graph. Let's check this.
Hello guys, welcome back to TechDose, and in this video we will see how to detect a cycle in a directed graph. So let us look at the problem statement. Let us assume that we are given a graph which is a directed graph with an adjacency list, and the number of vertices in this case are equals to 5. In order to solve this problem, we will be making use of the visited array, as you might have seen it in BFS and DFS techniques. The visited array size will be equals to the number it's visited this. So now we will visit all. So at one we will again, which is a big drawback, or make this true because we have visited this one now. Now we will traverse all the adjacent elements to one. Since there are no adjacent element, we will not do anything, and we will go back, that is come back from one. So while coming back from one, we will make this true as false. Now, when we are at this 0, we had only one element and there is no other adjacent nodes other than this one. So we will come back and we will backtrack from this one, and we will backtrack from 0 as well. So 0 has now been processed, and therefore we will make this as false again. Now, since this 0 has been processed, so we will now move on to the next element, which is 1. So we will be now at 1. So at 1, we will again make the fresh array.
Okay, so here would be like for right? For I is smaller than n would be prereq, would be prerequisites dot size, and then plus I. And then what I want to do here is do this, right?
which will be all false, and these are 0, 1, 2, 3, and 4. Now, first of all, we will visit this one, and therefore we
And then DFS. So the DFS will take, it will take, it will take the, it will take a vector of bool visited. It will take the adjacency list. Will it take the stack? So you want to go in 0, and then you want to go in this, and then you want to go in this, right? But to get to achieve this step, so you're at so effectively what you're gonna call here is like DFS and then at what the fuck is going on here? And then you want to hit him with visited, right? And you also want this to be a reference, right? Visited, and then you want to hit him with the visited, no, adjacency I. That's a vector. That do be a vector.
will make this true. So we will move on to the next node, which is node 2. Now for node 2, we will again make the next adjacent node is 1. So we will visit this one and we will make this one as true. Now we will visit all the adjacent nodes back will come here. Now this one has been processed. So we will move on to the
Okay, in that case, I don't think this is a reference, right? Because you don't want the visited to the levels to carry onwards or like to backtrack. When you backtrack, you want it to be at the previous state, right? So you don't want that. And then after this, what you want to do is with this, then you want a result. Then you want result I to equals to true, right? Something like that.
next node. We will move to cycle. In a please rewrite of edges have already been
Right, I get it. Okay.
defined. Either is denoting the number of vertices
Okay, here we go.
and ADJ is the adjacency list.
So it simply takes visited and the list. All right, I'm with you.
Now here I have all
Do this.
already made an array visited, which is containing all the false values. Track of notel for cross array at I is denoting all the
I is smaller than equals to visited. So it's a BFS. Okay. I'm with you, sir. I am with you.
Which will keep track of whether a true value was returned or not. As soon as a true value is returned, we will come to know that a cycle exists. Okay. So for that reason, I have kept a flag variable. Now I will process each of the vertex one by one. So starting from 0, I will process.
So this is a vector. Right? Then I question, do I even need to have another, like, can I just do this? Right? So for this, I can just do this. Right? Okay.
This node 0. What I will do is I will make it true since we have assumed that the processing node is visited.
And then I will make this true. And I will go into the actual thing for j equals to 0. J is smaller than adjacency I. Right, now I'm into the next one. And then what I want to first check is if adjacency I j is equals to true, right? And if it is, then I just want to return false. Right.
Okay, so we have visited it, and then we will visit all the adjacent nodes by using this adjacency list. So adj at I is denoting all the adjacent nodes of this node I. Now we will iterate through all the nodes and we will use this utility function. Now each of the node will be sent to the utility function one by one. This is the adjacency list. This is the visited array. And this is the current node which we are processing. Now, if the current node which we are processing has already been visited, then that means we will return true because there exists a cycle. If the current node being processed is not visited, then we will make this true, and then we will again use that flag variable, and again we will call its adjacent nodes, and we will process its adjacent nodes. Okay. And after
So
processing,
it's just a depth first search, man. The fuck? Then what is going on? What is going on? Okay, this guy's confusing me now. Okay. So it is a DFS. And then I'm feeding in the what exactly? Okay, this is so confusing. Okay. DFS, topological sort, right? And then cycle, detect cycle, right? Okay, let's just do this. Let's just do this, right? Okay, so function to perform. Okay, edge. Oh, what the fuck? I don't understand it. I understand it, but I don't know how to code it, you know? Um, I guess I can just look at the neat code, honestly. I feel like the neat code would make the most sense. Okay, neat code for schedule, right? And we can learn this together. Serves, right.
Hey everyone, welcome back. Let's write some more neat code today. So it is possible to complete. So once we finish course 0, then we're allowed to take course 1, which has no other prerequisites, right? The only prerequisite was course 0. So therefore, both of these courses are possible to complete, so we can return true. So let's look at an example where it's actually impossible. It's a neat version because I like it better. So, and I'm going to show you just the depth first search version because I like it better.
Sure.
So given this new example, the first thing you want to do is visualize it. So I'm going to draw a picture. So we're given 5 nodes. So we have 0, 1, 2, 3, 4. That's 5.
Okay, to take 0, you first need to take 1. Wait, what? Huh? You must first take course B if you want to take course A. Yeah, so B precedes A, right? So shouldn't it be 1 to 0? Shouldn't this be 1 to 0? Shouldn't it be all like 流翻轉? Okay, I guess it doesn't matter.
5 nodes. We're also given 5 prerequisites. So in this case, we end up having 5 edges, right? From 0 to 1, 0 to 2,
I guess it doesn't
1
really
to
matter,
3,
right?
1 to 4, and 3 to 4. So my goal here is for each of these nodes, I just want to know, right, for each of these classes, can we complete this course or not? And how do we know if a course can be completed? Well, just looking at this picture, it's obvious, right? 0 has a prerequisite of 2, but 2 does not have any prerequisites, which is great. It also has a prerequisite of 1, and 1 has 2 prerequisites, 3 and 4. 3 has 1 prerequisite of 4, and 4, luckily for us, does not have any prerequisites. So looking at this, it's kind of obvious that we can complete all these courses. So let's do the algorithm to be able to determine that. We see that these are kind of our base cases, right? 2 and 4
Yep. These
don't
are like the
have
leaf
any
nodes.
prerequisites.
Yep.
That's useful information, but
Yep.
we don't need a graph to tell us that. We can use a data structure called an adjacency list, and I'm going to call it prerequisite map because the data structure I'm going to use is a hash map to represent this. So for each of our courses, we are going to have a list of all of its prerequisites. So for 0, we know 0 has 2 prerequisites, 1 and 2. And we're going to repeat that
So
for
an
every
adjacency list.
run 0. So we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have our prerequisite map. So we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1. We see that it has 2 neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then
Then I'll DFS into visited and then adjacency list I. Right, then I'm feeding him the 0th. And then I'm gonna be feeding him the first. And then the second. I'm not sure.
And we want to look at the course cut can be completed. We're able, we know and from 1 be completed. And now it can be completed because it is a prerequisite of 1. And since we already know 4 can be completed, we can get rid of that as well. So now we know for sure that 1 can also be completed. And now even 2, like the loop, I'm going to use one last data structure to complete these courses, but how can we actually detect this loop? I'm going to show you how really quickly. So to detect a loop, I'm going to use one last data structure, and it's going to be a set, though I think you could just use an array if you want. I'm going to call it the visit set. And so now we visit 1. So we're going to add 1 to our visit set, and we look at the prerequisites of 1. It has 1 prerequisite. To do that, we have to first lastly 0. And
We should be with this, right?
And so these create our pre-map, so our list of prerequisites. So we know for each course, we're still getting a cursively function because then we'll have access.
Takes number of courses, prerequisite list of list, vector of events. So that's the adjacency list itself, right?
To all these variables without having to pass them in as a parameter. The only parameter that we have to pass in is the current course that we're visiting. And so, like most recursive functions, we want to look.
Okay, I'm just gonna look at the solution for C++. Because I feel like I already understand the solution, I just don't know how to fucking do it, you know? Um, yeah, so I fucking suck ass. All right, so let's look at this. Map each course to its prereq. All right. If not, else return true, right? Okay. Sure, okay. And then now I'm here. For bool DFS, it takes an int, right? Of the current course. And it already has the map, so this map will need to be inserted as well, right? What else? And visiting as well. And every single eye, there should be a new visiting. Sure, right? Which is the current map, right? and then iterate through all the courses, right? Okay, sure. So I'll pass in visiting as well. Int visiting, right? And this would be that. Adjacency list would be that as well. And then if current course is no. Visiting dot count of current course is not more than 0, is not 0, not 0, return false. Sorry, count, and if it can find something, then you return false. Right? Yep. Else if adjacency list current is empty, and you also return true, right? Because there's nothing else for me to depth first. Sure. And then I insert current. Sure. Or in the adjacency list dot current, and then I'll if DFS pre is not true, I'll return false. And then after it's traversed everything, visiting dot erase everything. Erase CRS. Okay. Why would I want to clear that? Why would I want to do that? Well, that's the part I don't understand. But let's run it to see if it's right first. Just disappear. It'll only take me and you. It's a vector, right? Vector dot size equals 0. It's not a structure or union. What? What's wrong with that? I don't know what's wrong. This shit is fucking blowing my mind out. Let's just ask Rock, you know? I want to know what the fuck's wrong. Bum, 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 bum. Just disappear. Bum, 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 we could set the night to music. To music, we could do what you wanna do. It'll only take me and you to set the night to music. Physics, shit. Well, there's none courses, so. All right. And then I'll DFS the graph itself, which is the adjacency list. And then what was it? Hmm. Hmm. Okay. Build graph, I've already done build graph. Okay, and then this, let's see. It takes what? It takes current is last. graph returns this, right? Right, and this would be that. Right? And then if visited dot currently, I'll return true. And then I will visiting dot CRS true, right? Visited as well. Visited in Notla, like that. Nope. Why? Referencing binding to null point. Mm, 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 mm. It'll only take me and you to set the night to music, to music. We could do what you wanna do. It'll only take me and you to set the night to music. 邊度錯啊？Come on now，我真係唔知啊，to be honest。我真係唔知。I'll ask the fucking AI. I want to find a working solution and then I can slowly reason through it, like line by line, so I fully understand how to code it. Like, and then I'll code it again tomorrow, you know? Like, I don't fucking know what the fuck's going on here. I really want to move on to the networking stuff because I have a lot to go through, to be honest. Also, by the way, how is Aaron Gordon so nice, huh? Like, this man be on one, though. All right, let's see. What's wrong? Mm-hmm. Mm-hmm. Oh, is that why? Could that be why? Could that be why? Oh my God, it is. No way. I thought it resizes automatically. What? Okay. All right. Let's go to Nicode's example, right? So So I would want to share my iPad screen, but I'm not exactly sure how to do that. Mirror iPad screen to Mac. Yeah, how do I do that?
We'll guide you.
Wait, isn't there a thing that I can do that with? I swear there is. Mirror, right? Oh yeah. Oh no, 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 no. Okay, but that's not what I want. Uh, because what I want is actually iPad mirroring. Can I do that? Cool. Okay, but do you guys see it? Do you guys see my screen? Um, let's say if I go like, oh, I can do this. Oh, no way. No way. Okay, let's see if this works. Oh, wow. Okay, I see. This is beautiful. Okay, here you go. Okay, so now you can see my screen, right? Yep. Okay. So let's go here, right? All right. New page. And then, all right, so this is the current setup, right? The current setup is 0, 1, 0, 2, 1, 3, 1, 4, 3, 4. Right? These are the prereqs that we have. All right. Um, and then, okay, you can see it. Okay, beautiful. And then, so we have the adjacency list. So we create the adjacency list via this. So we have a vector, right? And then it will be 0, 1, 2, 3, 4, right? And these are indexes. And then 0, I'll put nothing, right? And then I have and then I have a vector which is 0, 1, 2, 3, and 4, right? And then at 1, I'll put 0. At 2, I'll put 0, right? At 3, I'll put 1. At 4, I'll put 1. And at 4, I'll put 3. Right? So that's the thing that we have here. This is our adjacency list, right? This is what we currently have, right? So these are the indexes 0, 1, 2, 3, and 4. All right, cool. And then I will have a visiting vector of bool. Visiting, which is set to false, 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 and false. And I'll have another called visited, which is false, 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 and false. Okay, cool. I'm just running through the algorithm here. So, yep, cool. So we have everything we need, right? We have the adjacency list, and then we have the visiting vector and the visited vector. All right, so what do we want to do now, right? So for I equals to 0, I is smaller than num course. So I'm iterating through all courses, essentially. So if visited I is not true, so this is false, this would be true. If visited I, okay, let's go to here first, right, to understand what really is going on here. So it's false, and then I'm passing this through, right? DFS adjacent visiting visited I. All right. So DFS logic. Right now, I'm passing through DFS adjacency visiting visited and then 0, right? And then if visiting current is true, visiting, right? Then I'll set it to false, which is not, right? It's currently false, so it's fine. And if visited is equals to true, then I'll return true, which is not, so it's false. Okay, and then I'll set these two to be true, right? Sure. And then I'll tap into the adjacency list of, okay, wait, let me draw this graph first. So it's 0, there's nothing. And then 1 will be pointing to 0, right? 2 will be pointing to 0. 3 will be pointing to 1. 4 will be pointing to 1 and 3. So this is the graph that we're working with here. Pretty cool. Right? Yeah, I think that makes sense. Okay, so now we are visiting 0, right? And then I'll set visiting to visited to true. Boom. Okay, it is. And then I'll traverse and I'll pass in these two to the next call, which is DFS V and 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 whatever the neighbors of O, right? Um, However, so this will be what's passed into here, right? However, this is empty. So there's really nothing. So what will really happen here? That's my question. So visiting current, no, so this will just be skipped, I believe. Right. This will just straight up be skipped because there is no pre in adjacent zero, right? Because the first for loop will be skipped because there's nothing. So there is no call here. There's no call here. Skipped. And then visiting current will be set to false. Visiting current will be set to false again. And then it will return true. Sure. So this will return true. And then it will be set to false. Return true. Visited I is now true. And DFS, so this is true, right? So it becomes false, and this is also true, and it becomes false. So this will not happen. False and false will be equals to false, right? And then now I'm going to the next one, which is 1, right? So this in visited, right? So this is done. Now I am at 1. So what will happen in 1? So right now, the call stack will become 1, right? If visiting current equals to 1, return false. Visiting current is false, so it just skips. If visited current, return true. No, it's false, so I don't return true. So now I will turn these two into trues and trues, right? Right? And then I will pass in a recursive call adjacency V and V and neighbors of 1, right? So I'm sending these ones in now. Boom. Right? And then so the next call will become this. A, V, V, and then 0. However, 0 in visit Ted, I've already visited it, so it's true. It just returns true. Boom. Right? So it's gone. And there's nothing left. Right? There's nothing left. Therefore, I will set this back to false. And then I will set visited. Oh, visited is already set to true. Right? Okay, cool. And then this call, this shit will return. Right? And then this one will return as well. Visited I, that's before, right? So it doesn't really matter. I wonder if this works. Does this work? Does it work without that condition as well? Right? It does. Okay, yeah. I was thinking like, isn't that a bit redundant? Okay. Anyways, so yeah, it returns one is passed, right? And then now I'll go to two. Are you still following? Right? Okay, you're still following. And then now I'll go to two. So one is visited. I'll mark that as visited. And then I'll go to two now. And then for two, visiting current is false, right? Visiting current is false. Visited is also false. So now I'll set these to true, right? Set these to true. And then what I'll do is pass in the neighbors, right? Neighbors of two, which is this, 0, right? And then if I pass in 0, which is the next call, right? If I pass in 0, 0, visiting is false. However, visited is true. So I'll return true. So this returns, so this call returns true. Boom, gone. Right, so it does not return false. So the upper level does not return false. Oh, yep. And then it will pass through all of the neighbors. And then this call is done. Boom. And then I will set, wait, what? Oh, this one should be true, right? This one should have been true just now. And then now I'll set it back to false. And I'll return true. And then this goes on and on. I believe that just goes on and on. 3, right? And then boom. Oh, sorry, boom. 3, false and false. So I'll turn to true and true. And then I'll pass in the neighbors of 3, right? Neighbors of 3, which is 1. And then 1 visited already is true, so this returns true. And then goes to all the neighbors, which is no more, so this will be set to false. And then it'll return true. And then finally, number 4. And then number 4, it's false and false, so this will be set to false. Set to true. This will also be set to true. And then passing the neighbors, right? A, V, V, N of 4, which is 1, A, V, V, 1. This is true, so it returns true. And then it'll pass 3. 3 is true, so it's already true. So it's true and true. And then I'll set this back to false. And then we will be done. And then the main function will just return true, right? Okay. All right, cool. Now, okay, I set my own test case I can set my own test case, right? I believe. Um, in fucking, right. Okay, so prerequisites, I'll go, um, we'll go, right? 0, 1. 2, 1, 3, 1, 4, and 3 and 4. Number of courses is 5, right? And I'll do another one, another test case. Let's say it's let's say if it's what if it's this? Would this work? No, this would work. This would work. Right. So what if I create a cycle here? Right. So let's say if this one becomes this, right? What happens there? So 1, 4 will become 4, 1. All right. So in this case, it would fail, right? Because this cannot happen. This cycle creates an infinite loop, makes it a cyclic graph, so it doesn't work. It shouldn't work, right? So now it becomes 4 and 1, right? So what happens here? This would be pretty interesting, okay? So 4 and 1. So in 1, I put 4, right? So in 1, I put 4. I put 4. Cool. Cool. All right, so let's do all this again. All right. All right. All right, cool. So this is what we have. And these will all be set to falses again, right? So let's run through the algorithm again and see how we figure out there is a thing, right? So first we create the adjacency list. So it's the same procedure, right? You do this. And then now you go through, you create these two vectors, which is false and false. And then you go through the neighbors, right? So you DFS call A, V, V, 0, right? A, V, V, and 0. And then 0 in visiting is false, so it's false. So you ignore. And then uh, visiting in and 0 in visited is also false, so you don't return true. So now you set it to true and true, right? True and true. And then now you pass in all the neighbors, which is nothing, so you skip it. And then you just set this one to false. Boom. All right, cool. And then now it's 1. So, and then it just returns true, right? In the main function. And now it becomes 1. All right, 1 in visiting is false. So you don't return false. It's also false, so you don't return true. Therefore, you hit it with the true true again, once again, right? And then you pass in the neighbors, right? This is where it gets interesting. You pass in the neighbors, which is first you go 0, right? And as we all know, 0. And so 0 is 0 is here, right? So you return true for this call. And then now you pass in 4. And now you pass in 4. 4 is false and false, right? As you can see, false and false. So what we do here is we set this to true, right? And then we set this to true as well. And then I'll pass in neighbors of 4. Right? See, as you can see, the call stack is getting deeper and deeper. Pass in neighbors of 4. So I will first it will be 3, right? Because here. So DFS 3, and then DFS 3 is false and false. So you would change them to true and true. Right. And then you pass in the neighbors of 3. What would happen there? Neighbors of 3 is 1, right? All right, let's see 1. Oh, shit. 1 in visiting is true. So this would return false, right? Those would return false. This will return false back to here, right? This one, this call you're passing in as neighbors of 3. So in the 3 call, you would return false, right? So you return false for this one, therefore you return false for this one, therefore you return false for this one, right? So in the main function, you simply return false, right? That's how we recursively make it so that we find the falses, right? So that kind of encapsulates what's going on here. So if you come back to here, I kind of walked through the whole algorithm just now. And then yeah, so the test cases that I just talked about, right? It's this one. This should come in. This should return false. This one, 1, 4, should return true, right? So let's run it and see. This should be true, and this should be false, right? Yep. All right. I think I spent quite a lot of time on this one today, so I'll call it a day here. I'll code it up again tomorrow just to make sure I kind of understand what the fuck's going on. But yeah, I think overall I got much better at this just by spending a little bit more time on this. Topological sort, depth first search, pretty damn interesting. These like Gantan halls are going to be kind of annoying to deal with, you know. But yeah, I think it shouldn't be too difficult. Now that I've walked through it and fully understand it, I think I get it now. Yep. So peace. I will get back to my networking stuff. Said networking stuff is like Cisco Packet Tracer, like that sort of shit. So I really want to help my girl out. So yep. Peace. See you tomorrow. JBBNT. Jayo, my friends. Wish me luck on the job as well.